All right, maybe let's start. So good morning, everyone, and thank you for inviting us. Thank you for the organizers for giving us a chance to come over here in this beautiful place. Actually, I came here several times as a tourist, but this is the first time that I come here on a business trip, which is a great occasion. What I would like to do in this hour or so is to share with you some of the views, some of the developments, some of the research, and not only research, but also how we're actually pioneering and experimenting with AI technologies in various industries, but I will put more focus on the tourism and the travel industries, as this is the focus of what we're talking about. So actually, I work in Zurich, in IBM Research. Most of you know about IBM, obviously, but probably you don't know much about IBM Research, which is actually the organization I come from. So this is IBM. We like to think about IBM Research as the innovation engine and the driver of the longevity, the differentiation of the IBM company. And as you can see, these are the different labs of IBM across the planet. We cover basically every continent. Zurich is the center there where I come from. And it's also one of the largest, probably the largest industrial research organization with more than 3,000 scientists. Over 1,000 of these people are doing work that is these days related to AI. So quite significant investment and a significant focus, and more than $6 billion per year of investment in various research and development activities. We don't hear much probably about IBM Research because, as I said, it's the innovation engine that is driving every IBM product and every IBM solution. And over the years, as you know, IBM is a 106 years old company, so it's not a young company, but it has always transformed itself, in particular through its research organizations with the great achievements that we saw here, some notorious ones like Turing Awards, and Turing Award is like the Fields Medal in math. There's no Nobel Prize, as you know, in math and computer science. So for computer science, there's the Turing Award, and for math, there is the Fields Medal. But most notorious ones are the 6 Nobel Prize winners that research, and actually 4 of them are in Zurich. And if you wonder why they are in Zurich, some people did some research. This is an interesting chart, just for the sake of humor, that illustrates the amount of chocolate that is consumed by capita and the number of Nobel Prizes per capita. So it seems like a strong correlation between consumption of chocolate and Nobel Prizes, which obviously doesn't explain completely why we have most of the Nobel Prizes concentrated in Zurich. But anyway, this just shows that correlation is not causality. And statistics, as one of the great statisticians said, statistics are like perfumes. They are to be sniffed, not swallowed. Okay. So anyway, let's go back to AI now and our focus. So before we go into the AI world and AI development, it's important to understand why actually what's happening now is not a chance. And there are just waves and eras that come and go in computing. And what we're experiencing now is a really new era. And we understand that better when we step back and take a historical perspective on the evolution of computing. So, as you know, computers or computing in general is as old as humanity. Humans always wanted to find ways to work with data. And the driver has always been how to record or store information, and then how to process it and use it for whatever purpose. It has always driven, actually, the evolution of computing. So when we hear about big data today, there's nothing new about big data. Big data has always been the driver of computing forever. So at the end of the 19th century, when let's say, in the recent times, the most recent, let's say in the last centuries, machines that were introduced, like the tabulating machines, you remember, everybody knows, or some of us maybe even remember the punch cards. The origin of that technology was introduced by a gentleman called Herman Hollerith at the end of the 19th century. And the reason why that computing models, that punch card models that we know was introduced, it simply was at that time because of a big data problem of that time. And the big data problem of that time was the US census. Every 10 years, the population was censed and calculated, and it used to take 8 years to process the census data, to count, how many people, how many females, how many males, the various age ranges, etc. So that was a true big data problem at that time. So new computing models had to be introduced, and that's how this gentleman who founded the company at that time, that later became IBM, that we know today, introduced those systems because of a data problem. Then these computing systems kept going until around the mid-19th century when, again, a gentleman by the name of John von Neumann introduced a new computer architecture, also in conjunction with the advances in electronics, with the invention of the transistor and other things. A new type of computer architecture was introduced simply because, same problem, a big data problem. Data was physically stored into those cards that were punched. So how much data and how much programs can you store in those kind of media or devices? Again, a big data problem that called for new models and new ways to store data, process data, and use it. So that's how the programmable systems that we know today, just like my computer and every one of your computers, actually is built after the von Neumann model. It's all programmable systems that we actually program in the sense that we give them a set of exact and precise instructions what to do on data in order to produce some output that is unambiguous, that is either true or false. So the systems are highly grounded and completely governed by logic. That's why everything is zeros and ones. So now, the type of data that these machines were built are typically transactional data, tabular data, structured data. The problem is with the more recent advances in various technologies, in communications, the internet, and so on, there is more and more information that is either digitalized or created that is not structured. It's not in spreadsheets. It's not in tabular forms. It's not in databases that you can talk to in a programmable fashion and select a set of customers and count how much they bought and calculate the balance in your bank account and all of that. All things that we do through programmable instructions, through logic calculations. But again, if you look at all the types of data we have about, take images, video, text, how do you write a program that tells you whether there are cats and dogs or there is a happy child in a picture? It's very hard. What kind of instructions in logical rules you're going to put in a computer that will tell you there is a happy child or a happy cow in a picture or not? That's very hard. So again, but we need to make sense of this type of data. Why? Simply because it represents more than 80, or some people say even 90% of the data that either we create or we consume. That is unstructured data. Text, speech, images, videos, etc. So again, we're hitting a barrier here. And a new type of computers and computing needs to be introduced. And that's why we're talking about a new generation of systems that we call cognitive systems or AI systems. And these systems are not typically machines that we program with logical instructions, but these are machines that we teach that learn from a large number of observations. So instead of writing a set of rules, of logical rules that determine if there is a happy cow in a picture or not, we'll just present the system a very large number of examples of pictures of cows that are happy, not happy, and we have a lot of cows in Switzerland. That's why we talk about cows. A lot of pictures. So, and that's how the system will learn how to recognize. But it's not going to be. This is very important to understand. The answer or the output of this system is not a true or false. It's a probabilistic output. It's very likely to be a happy cow or not. So there's always a probability that comes with it. There's a confidence that comes with it. In a sense, very much like humans. Sometimes, you look at an object, or you look at a scene, or you look at a text, and you're not sure about the meaning. You may read the text and what's the actual, so you just make some sort of estimation of the meaning or estimation of that object. Of course, the likelihood or the confidence is higher as the ambiguity is lower. But the more ambiguity there is, the more probability, I would say, is there. So I assume most of you have seen examples of the Watson system, but this is just an illustration of probably the first system of this kind that was built, and it was built again by IBM Research in a few years back. That shows
Jeopardy.
actually.
What do you say we play Jeopardy? All right, let's get right into the Jeopardy round. These categories: a man, a plane, a canal, Erie, Chicks Dig Me, children's book titles, My Michelle, MC5, and finally, vocabulary. Ken, you're in the first position. Please make a selection.
I've never said this on TV. Chicks Dig Me for 200, please, Jimmy.
Kathleen Kenyon's excavation of this city, mentioned in Joshua, showed the walls had been repaired 17 times. Watson.
What is Jericho?
Correct.
400, same category.
This mystery author and her archaeologist hubby dug in hopes of finding the lost Syrian city of Urkesh. Watson?
Who is Agatha Christie?
Correct.
Anyway,
Same
I'll
category.
stop here.
What do you say we play
You
Jeopardy?
probably have seen this.
Let's get right into the...
So here, the machine was playing against two of the best players of this TV show, two of the best players of all time. And it beat them big time. You can see this on YouTube. I'm sure most of you have seen it. But it's just to illustrate that these types of machines, actually, they understand that natural language that I was talking about. They understand both structured and unstructured data. And they understand the questions, the cues in the question, and then they generate a set of hypotheses. And as you saw in the responses of Watson, there's always a confidence that goes with it. So just to give you a sort of working example of what is an AI system, these are the things that I highlighted in looks like orange. In this definition, the key thing are these systems, again, They learn to perform some task from observations. So what this means is that as we build these smart systems, these AI systems, they are not going to be systems that are for general purpose, but they will be highly specialized in and highly trained in the domain of interest, or the domain where they specialize. So an expert in, let's say, in tourism, or in medical industry, or in wealth management, in banking, or in insurance, is going to be, so deep, so specialized in that domain, but doesn't know necessarily much about other domains. So this is very different, again, from the general purpose machines that we build. We just process instructions, regardless of what those are, and they process data regardless of what data is. So we're moving from general purpose types of systems that we're used to into computing systems that are highly trained and specialized. So you may say, all right, well, building these machines is tedious, expensive, and how much actually, who can afford these kind of systems? And the answer is everyone. There are three reasons why these technologies are becoming real and becoming extremely affordable. And I'm going to walk you through these three fundamental trends that are making these type of systems a reality in every industry, in the tourism industry, in every single industry. So the first one is, most of you probably know about Moore's law. Moore's law is the mother of all laws in IT. Basically what it says, every 18 months, whatever computing performance you're getting from a device of some size, you're going to get double of it from the same size. And it's going to cost half the price. Right? So if you take a computer system like Watson, that system that you saw playing Jeopardy, so that was a very large computer. It fits in a large room. It cost millions of dollars to build. But then, if you look at how Moore's law actually is shrinking the sizes of computers and the size of computing, and at the same time multiplying that computing power at a very cheap price, you realize that, for example, a computer that can do 1 teraflop. 1 teraflop is just 1 trillion operations per second. That's how fast a computer can go. In the 70s, it used to take 10,000 Crays. Crays were the supercomputers of that time. They cost millions of dollars. Now you get this in an Xbox. An Xbox delivers 1 trillion of operations per second. It costs about 200 or 300 euros, right? So some of the latest smartphones, basically about 2 or 3 of them would fit in a teraflop. So now, if you think of this exponential trend, humans are not very good at understanding exponential trends because we have evolved in our evolution at understanding linear trends. So we think it's going to be 2 and then 2 and 2 and 2. But actually, this is exponential. To give you an idea, if you take probably one of the largest or the fastest supercomputer that exists today, which is 20,000 times a teraflop, we call it petaflops. How much time is going to take for this computer to fit into an Xbox or to fit into something like this? The fastest, most powerful supercomputer on Earth today. The answer is, it's going to be in about 12 years or so. So you can imagine, but then the interesting question is, these devices, or computers of this power, one teraflop, where would it fit in 10 years? how small it's going to get and where it's going to fit. And the answer is, it's going to fit basically in every cellular tissue of the human body. So you can deploy a complete supercomputing network inside your kidney, inside your lungs, inside, in any organ of your body. And of course, you have to be careful about security, not to get hacked, or somebody may, mess up with your lungs or with your kidneys. But obviously, security that goes with it is important. So this is one of the fundamental trends that is actually driving very, very hard the adoption of all sorts of new technologies. I mean, there are other things like quantum computing, blockchain, etc., that we're not going to talk about. But AI is one of the technologies that are being driven by this kind of trends. And it's not stopping anytime soon. But then, one interesting question that comes up here is, okay, we're going to make a supercomputer fit into a lung or a kidney. But how are you going to power it? Where is it going to get its energy from? Of course, it has to get its energy from the human body. You cannot plug wires and batteries everywhere. So we are actually working on developing new technologies, new types of chips that are powered by liquid. So very much the same way as the human brain works. So the human brain is the supercomputer. There's no more performant supercomputer than the human brain. And I think it's going to be the case for a long time. Okay, computers can count faster, but if you ask a computer, is there how much it takes a computer to find out if there is a cat and a dog in an image, humans are so fast at this and so reliable at this that, we're not fast at computing, crunching numbers, but we are very fast and very good at recognizing situations, at reasoning, etc. So, and the human computer, that is the brain, is powered actually by blood. Blood actually serves two purposes. It feeds the energy to the brain, and it also cools it down. So exactly the same mechanisms that the brain uses, we are porting them into chips that actually are both powered and cooled down by liquids. Right? So, and these things, again, remember that exponential growth. These things are coming very, very fast at us at very fast pace. So that was trend number one. Technology, computing evolution, and miniaturization and dissemination everywhere. The second one, remember in the definition of these AI systems that we talked about, the system requires a lot of data about a given domain, about a given task, in order to learn from that data and become experts in that domain. So you need a lot of data. But the good news is there's so much of it. In every domain today is either digital or highly digitalized. So there's so much information now about anything. So there will be no shortage of data going forward. And if you look at these projections, I'm sure you have seen various projections of this chart, whether it's 165 zettabyte or whatever, it doesn't matter. It's the exponential trend against that matters. And the interesting thing is, as you see here, at the lower part, most of the structured data that I was talking about, structured data that fits in tabular form, in spreadsheets, databases, etc., this is actually a small fraction of all the set of data, the types of data, and the amount of data that is generated either by the Internet of Things, devices and sensors that are collecting data about anything, multimedia, videos, speech, etc. But the bulk of these, as you see, are unstructured. The structured part is mostly this lower part. So that is, I don't discount the importance of structured data. It is critical for decision making in every business. And businesses still rely very heavily on structured data. But the point here is there is more and more types of data that complement actually that structured data. We call the upper part the dark data simply because it's not visible to typical computers that I was talking about. So data is everywhere, and there will be plenty of it going forward. By the way, when we talk about an exabyte, which is 1,000 of petabyte, which is 1,000 of a gigabyte, you can fit a video TV quality in 1 gigabyte, right? An exabyte is, think of every human on Earth, there are about 7 billion or so. Every human would carry 150 books of the size of the Steve Jobs biography, for example, 7 centimeter thick. So that's the amount of information that is an exabyte. Every human on Earth carrying 150 books of that size. If you pile up those books, one after the other, it's actually 3 times back and forth the distance between Earth and the Sun. That's what fits into an exabyte. That's the type of storage capabilities that are available today. Right? So remember that Moore's law, that exponential growth, doubling every 2 years or so. So that's the kind of, of amount of data, that's coming to us. The other thing that is less talked about and less known, remember, we talked about the hardware and the acceleration in miniaturization. We talked about the abundance of data. But then there is a third component that gets us closer to what we're going to talk about in the rest of this presentation, that is software, new machine learning, a new machine intelligence software and algorithms that actually have known an extremely rapid development in the last decades or 20 years. And basically what's happening here is, again, it's a completely different way of working with data. Remember, when we had these structured, logical things, we could not make mistakes. And we still cannot make mistakes on structured data. I don't want an approximate number for my balance in my bank account. And I want an exact number, right? But actually, a lot of this processing of this unstructured data doesn't require the exact computing that we generally do. So there are new areas of development around what we call approximate computing that actually makes things go much faster and consume less energy. For example, if I ask you if 100 divided by 2 is bigger than 3 or not, it's obvious. We don't use much power in the brain to find that out. It's easy. But if I ask you if 100 divided by 13 is bigger than 7.692 or not, you will need a little bit more thinking, more computing power, right? So same thing here. We're taking those ideas, those concepts, and porting them into computing. So basically now we're building chips and machines that if you're processing this huge amount of data and you just need to do calculations like this, you don't need to do the exact division or the exact multiplication because actually you don't need that. So, and that's a new type of computing that is actually, again, is going to help accelerate this miniaturization, reduce the power. So when we feed those supercomputers in our lungs and kidneys, we don't have to power them the same way, and we need enough power. Probably we'll need to eat more, and drink more beer to generate all the necessary power to feed all these supercomputers, but probably that will help in some other respects for people who have more power to burn or more energy to burn. Same thing happens, again, on the software. We're building software and algorithms that do not necessarily calculate things exactly. So, for example, if you want to know what is the average salary of employees in India between the ages of 21 and 27, right? So there are a lot of DIJOUS, obviously, but are you looking for the exact number of the calculation of the average, or some approximation? If you are 5% off, it doesn't matter. That's enough. So again, trading off precision, 5% or 10% precision, but gaining so much speed and saving so much power in processing that huge amount of data is actually what we need. So if you combine these three things that I talked about, these are the fundamental technology trends that, that we talked about. Data, hardware, and software. Hardware and computing is becoming available to everybody at every volume, at any price you have through the cloud. That's what the cloud is all about. The cloud is democratizing access to computing power on demand, so people can actually access as much computing power they need, which is getting cheaper and cheaper. Same thing according to those trends. And the recent advances in machine learning, deep learning, we'll talk a little bit about that, but also accelerating things. So I wish acceleration in software part was as fast as the data and the computing acceleration, but that's not the case. Unfortunately, software innovations and software development is still a hard problem. It doesn't move as fast as we would like to, but it is actually accelerating. It's ramping up to a large extent because of more and more open software, more and open source is available out there, and developers are using more and more of those softwares, more standards, more interoperability between software. So it's like it may become exponential at some point, but now it's still at that sub-linear, or let's say linear part of it before it takes off. But I'm confident we're getting there. So this is what makes a perfect storm for AI. And if you still have doubts, or if other people around you have doubts, this combination of these three trends is not going to slow down. This is not going to go away because of these fundamental evolutions and fundamental developments that are going actually to shape everything we do in societies and in businesses. So again, as I said before, given all of this, so this is how big and how complex and how expensive was the Watson computer. But now, everything that used to make Watson, actually what we took it over the years, Watson now is a platform, is a cloud platform. Basically, what we did, we took all that big monolithic system, we decomposed it in a set of components. We call them microservices or APIs, depending on how you want to call them, and take all those different pieces and make them available for people, for developers, for businesses, to actually combine them and build systems that fit their industries, their use cases, that fit their ideas. Because no single company on earth can think of all possible applications of AI technologies. At the end of the day, the innovation is going to come from people who understand industries, who have ideas, who think differently about about doing things, about the process. So our job is to actually take the basic capabilities of AI and make them available in a cloud platform so people can go there, combine those different services, bring their own data or use public data, and then build this system, train these systems to accomplish some tasks in some specific area. So just to walk you through some example or the type of capabilities that are available out there. So a lot of this, as I said, we are actually barely scratching the surface in AI. You see all these advancements in various things. Chatbots are everywhere, and robots, autonomous robots, autonomous vehicles, etc. But we are barely scratching the surface, actually, as we understand how to better represent, parse, analyze data, especially that unstructured part, how we train these systems, how we interact with these systems. So, but the capabilities for, let's say, building what we call in an agile world, the minimal viable product to start with and to keep iterating and improving, the basic technologies are actually there for people to start working. And the other component to this is, as I said before, we're opening these technologies through platforms to everyone. So obviously, language is very important. We cannot just think that English is the language that people use to communicate, although it is a highly disseminated language. But being able to understand and interact and learn from specific language is very important, which is why Watson now understands several languages actually and continues learning and improving. So now let's get into a few more examples now, more concrete examples on what can we do with this type of capabilities in industries like tourism, for example. So I attended recently one of the largest retail conferences and consumer conferences. And basically there, most of the discussion was about, it was also to a large extent about AI, but what is driving customer experience? What do customers really care about when they interact with the brands or way they interact with information? And these four things came out like some of the key, nothing new obviously for you, but these are the things that, as a consumer, as a shopper or as a traveler, they're the kind of things that we usually care about. So search is important. So how can we make search much smarter than it is now? Or even simpler than that? How can we make just your information as a travel service provider or tourism service provider, how can you make your information more searchable, easily searchable and easily findable? Sounds easy, but it's very hard. Simply because you have a lot of these unstructured data, a lot of disparate data that actually requires much smarter technologies to ingest, parse, analyze, link, etc. So, and discovery. Users, more and more users now are interested not just at, what you have in your catalog, but we want to discover new things. Surprise us, surprise the user or the shopper or the customer with new things that they didn't think about. Recommendations, I think not a single day goes by that any one of us here doesn't get bombarded by recommendations of all sorts. Some of them are very good, some of them are less good, but we still care about smart recommendations. We all welcome great and relevant recommendations. When I get a recommendation about something that I really like, I love the application or I love the provider who gives me that recommendation. And engagement obviously is This is something that, again, with the recent development, the ubiquity of computing, now people can capture videos, run videos, identify videos of objects in videos on their mobile devices that cost virtually nothing. You get them for free if you sign up for a 24-month contract with telco. So you get all this communication power in your hands, and as a user, as a consumer, we are using more and more of that to communicate, to capture experiences, share them with others, interact with brands. And the brands that are really at the forefront of innovation are the ones that are engaging their customers, not just broadcasting content. Because I can go on a website and I look at the offering of a brand and I can buy, but I need more than a few buttons for, selecting product and clicking the buy button and the shopping cart. People want more conversational, more engagement experience with their suppliers. So again, nothing new here, but the question is how technologies like AI are transforming these type of experiences, and how these technologies are enabling new ways to deliver these capabilities to help with differentiation and user satisfaction. And I'm going to share with you some of the examples here that, so again, as I said, the examples that I'm going to share with you are examples that are imagined by people who are in their industries, who understand. It's not necessarily IBM or some other organization building that application. Although we build some applications, but again, think of that platform, cloud platform capability, where we provide the basic capabilities. At the end, it's up to the developers or the businesses to build the applications by combining these things in ways that are innovative. So I'm going to share with you one of the examples here that we did actually in the beautiful island of Lanzarote. It was a unique experience of how actually you can combine some of these components of this platform in order to build smarter assistants. As you know, in the last 2 years, especially in the travel and the tourism industry, chatbots and smart assistants have become ubiquitous and becoming more and more important. So let me share with you a video with an example.
En redes Kios hemos desarrollado el ISA Turismo. El ISA Turismo es una solución cognitiva para el sector turístico que permite que cualquier organismo de gestión turística, como puede ser un ayuntamiento, un museo, ofrezca a sus visitantes una aplicación móvil basada en tecnologías cognitivas, por supuesto IBM Watson, y desplegada en la nube. Gracias a la tecnología cognitiva, el ISA Turismo ofrece al visitante una experiencia personalizada. El visitante se comunica con ella en su propio lenguaje, le habla de sí mismo, de su viaje, cuánto tiempo va a estar, quién la acompaña, y la solución elabora un perfil que luego utiliza para hacer recomendaciones adaptadas a los gustos, a las preferencias del visitante. No solo eso, sino que también dispone de un chatbot basado también en IBM Watson que permite que el visitante haga preguntas tanto absolutas como relativas a la posición en la que está, porque el ISA Turismo utiliza beacons en conjunción con la tecnología de Watson y que permiten hacer preguntas como quién es el autor de esta obra sin especificar la obra, hasta preguntas muy precisas, todas ellas dentro de un sistema de aprendizaje cognitivo en la nube.
La aplicación es una aplicación pionera y repetible. Utiliza la cognición para enlazar al turista con el espacio natural. Sigue ese espíritu innovador y de respeto de la naturaleza que, sin necesidad de invadir el espacio natural, es capaz de informar en su viaje a través de los diferentes lugares al turista, informarle de los hechos más relevantes de ese espacio. Así, si eres un arquitecto, te contará los elementos más importantes de la arquitectura del lugar, y si eres un biólogo, te hablará de la flora y de la fauna que tienes dentro del entorno. En definitiva, es una total reinvención de la experiencia del cliente mejorando esa capacidad de interrelación con el entorno a través del móvil. Y esto es una aplicación que la podemos utilizar en este entorno tan maravilloso como es la isla de Lanzarote, pero lo podemos hacer en un museo, lo podemos hacer en una ciudad, lo podemos hacer en un parque de atracciones. Utilizar la cognición para mejorar la experiencia de nuestro turista.
Right, so it's a long video, relatively long video, but I want to share it with you because I think especially it's done in the right language. But it captures, some of the things that I was talking about. What users, what travelers, and what consumers are actually asking for, or what kind of innovations we can put out there to help enhance their experience using this kind of technologies. Some other examples that actually, there is probably one of the most consumed cognitive or AI service that we have on the Watson or the IBM Cloud, Watson platform, is what we call Personality Insight, which has actually what it does, it would read text that a person would write in a blog or emails or reports, and then it finds a number of traits of personality, in terms of openness, agreeableness, etc. So, and why these things are important, obviously, again, as I was talking about earlier, the multimodality of the interaction between the machine and the human is very important. So when we talk among humans, we communicate tone, we communicate emotions, we communicate an attitude, we communicate style. We don't just communicate a piece of speech or text or words. It's the context, the emotions and the empathy that we give or that we receive that makes the experience. So the question is, how can we capture more of that into a user interaction or human-machine interaction? And that's what this type of services or this type of AI technologies, as I said, these are services that exist out there, but we are barely scratching the surface. We haven't solved that problem, and it's going to take decades for these systems to realize their full potential and to get to where they are. And I tell you, decades, we know, simply because we are building them, and we know how hard is it to build them, but we know also that we're going to get there. So another example of things that you have seen is the introduction of robotics powered by AI in the tourism industry, in the hotel industry. You probably have, I'm sure you know about hotels that are completely manned or managed by robots in Japan. But that's just the robotic part. The interesting part comes in when you combine robotics and AI, that hardware component plus the software, the intelligence that actually engages the customer or the user, just like the Connie robot that was deployed in Hilton hotels in the US, or the same Watson powered robot called SEP in this case was deployed in Motel 1 in Munich for Oktoberfest. So, and actually the interesting thing is these robots, obviously, they interact, they communicate, etc. You can watch videos of all of these on YouTube if you search and you find them. Of course, they are trained to interact in a domain, in some specific topics. You cannot ask these robots anything that you can ask a human. But the interesting thing about these robots, although we may think they take that human touch out of the interaction, actually a lot of people feel comfortable asking some questions to a robot more than to a human. So they ask things to a robot that you wouldn't ask a human. but that's, that's how we discover, again, as we put these machines out there, as we interact with humans, we interact actually in new interaction patterns, new expectations, new ways to deliver user experience, not necessarily by replacing the concierge. And this is very important. This is augmenting what the concierge can do. You'll always have a concierge in a hotel because there are questions that no robot can answer, and you need to talk to a human. But there are also situations where you actually want to talk to a robot, not to a concierge, not to a human, for a variety of reasons. So we saw some introduction of these in the travel and hospitality business, but I think, remember, the chatbots and this type of autonomous systems are getting faster and faster into this industry, and I think we'll see more of them going forward. Just because, I come from a research place, so, I want also to give you some idea about why is it hard to build these systems, why I told you it's going to take decades before we have systems that completely understand and interact in a fluent way in something that is closer to a human, simply because there are still things that are very hard to understand by computers in interaction, in dialogue, for example. So if you ask a human, let's say you're talking to a human on the phone in the insurance industry, you ask them what is covered in car insurance. They will tell you something, and then you tell them, how much does it cost? That agent will understand, when you say how much, they understand that how much does the car insurance cost. Now, most of the system we talk to, they recognize the question and they give you the answer. But keeping that context of the conversation and being able to, at any point in time how the conversation goes, like, oh, everything costs so much nowadays. How much does this cost? So, you're talking to an agent or to a human in a way that actually computers don't understand yet because they don't capture that context. So you need constantly to find ways to interpret the various utterances, what we call an utterance. An utterance is just a statement, a phrase that talks about something, a question. How to capture these utterances, position them in context, link them. And these are very hard problems. Nobody has perfect solution to these today. Every large company that is doing AI research, like IBM and many others, every university that is doing AI or natural language, actually still pursuing these things very hard. So there's a lot of work to be done there. But what we have seen also in the last few years, and with great impact into the travel and the tourism industry, is the rise of applications that consume more multimodal data, if you will, not just natural language, text, speech, and data, but also images, videos. And this is to a large extent due to recent developments in what we call deep learning. I'm sure you may have heard about deep learning. Deep learning is just new technologies, new ways of doing machine learning, teaching machines to learn from examples. Remember, you want to find out if there are cows, if there are happy cows in pictures. So what you do, you generally build what we call a deep neural network, and you train that neural network by showing them so much examples of what you're trying to learn, and they build their presentations in ways that are similar to how the human actually processes data in the brain. So there's nowhere in the human brain a circuit that says, if this neuron and this neuron, then it's a cat. So it's all distributed in our neural network, neuronal system. So I'm not claiming that artificial neural networks are similar to biological neural networks. We're very, very, very far away from that. But the design of these systems inspired by this type of architectures, these type of models, we are able today, remember again, we are able today to build image recognition systems that beat humans. There are systems now, you can go on Google, on YouTube and check, there are systems now that are so good at recognizing objects, but certain objects, not every object. So, but simply because they were trained on so much data. Remember, data, computing, two things are making these type of things possible. And we can actually now perform this huge amount of calculations on very simple things like, this is one of the things that we've been doing. We call it cognitive fashion or AI for fashion. So basically what this does, we go out and look for all sorts of images, text about fashion, tags, pictures, etc. And what we do, basically depending on, remember that personality inside, depending on your personality, depending on your style, pictures of you, we're able to go around and build a sort of digital wardrobe for you. So what that means, if you buy a dress, for example, the system will look at your style, types of trends, but also what's available in the various shops and tell you, well, here is a pair of shoes that actually would go well with this dress that you just bought. And by the way, you can click on it and you can imagine all the commerce behind it. If you buy it now, you get a discount and all these kind of things. So this is what's called algorithmic clothing. You hear about this term? Just like, you have algorithmic trading for computers buying and selling stocks in stock market, which account now for more than 70% of transactions or more. Now we have algorithmic clothing, which is actually one of the emerging innovations that we see that would help us even, find out what actually, not what just fits us, but what fits us and what's available in different shops and how can I get them. So it's like building a virtual wardrobe and you just, pick up and buy on demand. So again, these things look like, science fiction. A lot of these things a lot of things that we see today were science fiction just tomorrow. Machine translation, for example. A few years back, thinking of a machine that you talk to in your own language and then it translates whatever you're saying instantly in any other language, was like, wow. Or a car that is driving by itself. Wow. It was science fiction just a few years back, but now it's a reality. So these kind of things are also becoming a reality. And again, because of that those exponential trends that we see. There's some other examples, like how we can identify people, etc. Now, some other things that are happening that actually are even more interesting. In all the examples that I showed, basically, you listen to speech, somebody asking a question, and then you translate it, or somebody writes a natural language statement, and you try to understand the meaning, the semantics, the nuances, and understand what you look into an image, you see what's in that image. Now, a new area, again, from a research perspective, these are things that are coming up, that's why, I come from research. I need to tell you what's coming up next. Areas where we don't just recognize digits or objects, but we recognize scenes. What's going on? So, wouldn't it be great if you had a computer that looks at the image like the one on the right and says, in this image, there is a lady and a child, and the lady is throwing a red or orange frisbee. So humans can do that very easily. So there's no computer that can do that today. Right. So again, this is all unstructured data. So how do you take this multimodal, unstructured data that contains so much information in it and structure it and extract it? So you can actually the computer can just look at a movie or at a picture and gives you a description of what's in there. So you can, for example, say, let's say I want to travel to some place, and I just want to ask the system or the assistant to show me all pictures of resorts or hotels in Mallorca where people are playing golf, right? So now you will find those only if they have a tag in them. Let's say somebody tagged golf course or somebody. But actually the system should be able to just look into these pictures and extract a description and bring back those. So that's like the frontiers of what we're getting. But again, it's not science fiction, We're getting there. We're getting there very fast. And some of the interesting developments, actually, we have now machines that, chips that are, again, these computers that are trained, so specialized at recognizing objects. So this is a chip, a small chip, very high performance chip. All it does, it recognizes objects. So this chip does not, calculate or process text.
Thank you. The north is connected. Here we go. Cipher 10 image classifier is ready on True North. I found a horse. I found a deer. I found a dog.
Anyway, so
I found.
this is just to illustrate. So the thing is, these chips, and this is, again, toward those trends that I was talking about. These computers, the chip now fits in the back of this robot. You say, oh, it's still big. But again, that's more slow. The same capabilities, the computing capabilities you get in this chip, those same capabilities, you will get them in 18 months on a chip that is half the size. In another 18 months, it's going to be half the size. So how many iterations you will need to get to a chip that is 1% of this size? 7. You take 100, divide by 2, and you divide by 2, divide 7 times, you get to 1. So you get from this size to 1% of this size in 7 iterations. Now, once you have that type of chip, you can fit it in. So sooner, very soon actually, we will see computers, supercomputers that we are putting in our pockets. Now this computer has one chip in it, one processor that does everything. But sooner we will see actually computers that have many chips that are specialized in processing some type of information and performing some type of operation, like those visual recognition, others will be for speech, for videos, etc. So because of this miniaturization trends that we're talking about, because of the abundance of data, we're able to train these machines and build these chips and miniaturize them and plug them in all sorts of devices. So again, these things are coming very fast, and we actually are building some of these. We have one of my colleagues called Keiko in our research lab in Tokyo is building an application. She's blind. She's an IBM fellow, the highest technical distinction in IBM. She's building a sort of application that helps her navigate through environments, by understanding, and describing what's actually going on. So, I think I overrun a little bit, so let me, I'm going to conclude soon. Oops. Lost presentation. All right, just to conclude, to give you a sort of glimpse about, where we're going. This is the...
Close your eyes and then open them. Look at the towel and Dad. What do you see? Tell us.
So anyway, so we'll be able to build this kind of device and truly change humans' lives and make actually human experience, whether it's, as a patient or as a traveler or as a citizen in general, more agreeable and more powerful. Now, I'm sure this is in the back of everybody's mind, the ethical aspects of this. So there is obviously a lot of discussion going on in this space, and there is a lot of questions, rightfully so. I think it deserves a debate, deserves that also that companies like IBM and others take responsibility and clarify their position about what we're doing actually in this space and why we're doing and how we're handling information. So, as I said, the purpose of what we're doing here is really not to replace the humans, but augment them, make the humans better and greater at what they do or what they would like to do. Empower humans. That's the purpose. There's no other purpose. And as we do that, we ensure that we always make clear that actually you own your data. If you're using our platform, our technology, the data is yours. We're not stealing your data from you and just asking you to approve something, and then we take that data and we do whatever we want to with it. The data is yours, and the models, trained models, those algorithms that we distill from this data are yours because you trained them, and they belong to you. Because these models, the power of these models, they end up capturing a lot of the intellectual property and a lot of the knowledge. So they belong to you. And that's the kind of very clear statement that we make. And obviously, security is important. Making sure that data is secure, systems are secure, and we have experience in building that. And we secure most of businesses on the planet and government. So anyway, I'll stop here. I think I took more time, but thank you very much for your attention.